Okay, so let's start today's lecture. Any questions about this? Okay, so we were left at KD trees. If you remember, let's recap the problem. This is we are given a set of points in 2D plane. Okay, we are given a set of 2D points, and our goal is to report a subset of these points which are in an orthogonal range. Okay, so we are in orthogonal range searching. Our goal is these are also called window queries, but this window query is basically the sides of the edges of this window are orthogonal to the primary coordinate axes. So these are called, therefore it's called orthogonal range searching. So given a set of points, our goal is to report the points within an orthogonal window as efficient as possible. A trivial ON solution already exists. It's trivial to test whether a point lies within this range easily. And if you test it for all the points, you have yourself an ON time solution. So our question is whether we can reduce this ON solution to better time complexities. And this is possible with the help of index structures. So the two index structures we are going to discuss are KD trees and range trees. And they build upon one-dimensional range searching. So if we had just one-dimensional points and we were given an interval in this one-dimensional case, can you report the points in this one-dimensional search efficiently? So there are different ways. I mean, if we have a binary search tree on the one-dimensional points, if we organize these one-dimensional points in a binary search tree, what we can do is we can conduct two search at the same time on the left point and left endpoint of the interval and right endpoint of the interval, and find the splitting node in this binary search tree, and then report. We go left. When we go left, we report all the right subtrees when we go left, and when we go right, we report all the left subtrees. These are the points that are going to be in the interval. And if you remember, you suggested that, I mean, if this binary search tree was in an array, for example, we can use a sorted array as a binary search tree. We don't need to conduct these two searches. Just search for the left endpoint, and after you find the left endpoint, you can go one by one towards until you reach the right endpoint. Okay, so you can also, but this is going to be log n time complexity. And actually, this in chapter 10, the interval trees and segment trees use a similar strategy. They only search for the left endpoint, the beginning coordinate, and then the interval and segment trees, they use a similar structure. They have the sorted points at the leaves, so they go from left to right on this array to do it. So what you suggested is a plausible approach, and it's used in interval and segment trees. But here, let's focus in this chapter. Let's go according to the book and imagine we have a binary search tree built on one coordinate, and let's make use of this information to build KD trees and range trees. Okay, so in KD trees, we use the following strategy. Since we can do search in one coordinate efficiently, at each alternating depths of the tree, we first look at the x coordinate, then y coordinate, then x coordinate, then y coordinate. So by alternating coordinates like this, we conduct our search within the tree. So in order to support such a search, we built the KD tree like this. Our first split is through a vertical line. We split the points into almost equal groups with a vertical line, and the next level we make a horizontal split, and at the following level another vertical split. So this becomes our KD tree until a single point is left. Okay, So I'm not drawing a 100% correct tree because these splitting lines, the vertical and horizontal splitting lines, they pass through the median point. Okay, when we are splitting with a vertical line, it passes through the x-coordinate of the point sorted with respect to their x-coordinates, the median x-coordinate of the point. Okay, so and similarly when we have horizontal splitting lines, they pass through points. Yes.
Hocam mesela bir tane çok büyük x koordinat var. Sonra işte 300 tane de çok küçük x koordinat.
Yes. Okay.
Tam ortasından.
No, it's median, not mean. So we are there are 301 points. We are going to sort them and we are going to pass it with the 150th point. Okay? We are not taking the mean of these x coordinates. Okay? So we are taking the median of these x coordinates. So we just sort them and pick we don't care about what the coordinates are. Okay? We just pick the middle one. So we guarantee each time we do, we split into equal halves. And the median can be found in linear time. So there's this Kate selection or median of medians algorithm, which is based on grouping the points into groups of 5 first. Okay, so the algorithm is like this. You have n points. You group your points into 5 groups, unsorted. They're unsorted. Okay, so you have unsorted groups. You just randomly pick 5 groups, partition into 5 groups, and you find the median of each of these 5 groups in constant time. So since there are 5 elements in this group, you can in constant time find which is the third element in this 5 group. So what you have is what you have yourself is n over 5 groups. Actually, it's this, I guess. So you have this many groups, and you have this many medians. You have found the medians of these 5 groups, and what you do is you find the median of these n over 5 elements, and you use this to partition, to filter out the rest of the. I mean, you just check. You filter out based on what this median is. You can filter out. This guarantees you at each time to get rid of at least 30% of your data sets. I mean, you cannot do half. If you do half, it's going to be, you are not doing sorting also. But the difficulty of this, it looks very much like quicksort in that regard. You find some median of medians, which is supposed to be a good splitter point. But unlike quicksort, it's not n log n. Okay, this kind of if you do the complexity analysis, it turns out to be something like 24n. Okay, I mean, if your log n is greater than 24, I mean, it's less than 24, it's no use. I mean, theoretically, asymptotically, it's a linear algorithm. Okay, O24n. Okay, so O24n is On. Okay, asymptotically, but in order this algorithm to work better than n log n, this log n should be greater than 24. So for very large, and 24 is a very large number. I mean, log 24, and should be very large so that log n is greater than 24. So you can also use an n log n algorithm. And practically, although this is a linear time median selection algorithm, in practice, I mean, it may perform as worse as an n log n algorithm. Okay. So we can say, but theoretically we can say we can find the median in linear time, and then this is we split these points, and at the end, what we have ourselves is a binary search tree. Each time the root at the root node we have this horizontal splitting line at depth 0. At depth 1, in the left child, we have an horizontal splitting line and another horizontal splitting line at the right child of this root node. And then each of them, the left child is another vertical line. So it goes like this. And when we are given a query, so such a tree, KD tree can be built in O(n) log n time. Okay. It's very much like a binary search tree, just we're alternating coordinates. And given a region, given a query region, this is how we proceed. By looking at the first vertical line, we check whether this region is, for example, the whole region. So, and also each intermediate node in this tree indicates a region in the 2D plane, possibly unbounded region, okay? So, for example, the left child of the root node is the whole half a plane towards this, and sorry, this is the right child. The left child is this unbounded plane. So, and this may be, for example, the right child of the left child. It's going to be a child of some. It's going to be a descendant of the root node at some level. So each region, each intermediate node and this is as you can see, it's a bounded region. So each intermediate node in this tree is going to have a designated region for it. And we don't need to store these regions actually explicitly. We can find these regions, these vertical splitting lines already define these regions. And we can find, by knowing its parent region, we can find it's the intersection of this, if this is a splitting line, for example, intersection of this, its parent with this line is going to give the region of the child region. So we can find the regions of child nodes by looking at their parents and by knowing what is the splitting line at that node. So we don't need to explicitly store the segments, the regions. So given a region like this is my query region. My query proceeds as follows. I look at this vertical, I look at the left child and see whether it's completely contained in this region or not. And if it's not completely contained, and if it intersects the region, so there are three cases. First of all, the region may be completely, this right child does not intersect this query region, so I don't conduct search on the left child at all. So I may completely filter out, prune the left region. So this is one case. Another case may be a certain region here, maybe, so this is, imagine there is a KD3 region. A region may be completely inside this query region Q. In that case, all the points in this region can be safely reported. And if not, the third case is the query region is intersecting intersecting this query region. In that case, I continue searching in this child node. So I continue my search with the right child of the root. So it's going to, this query region is contained within this right child of the root. So I'm going to continue my search within this right child. So the depth of the tree is log n, but now if we think about the running time of this algorithm, we may need to bound the number of regions that are intersected by this possible query region Q. Okay, so how many regions, if it was a point query, if this region Q was a point, okay, if my region was very small, it was like a point, the query time would be log n. Okay, it will be, you would be going, each time you are going to choose one of these, since it's divided by 2 each time, since the depth of the tree is log n, you are going to end up at some node at the end. But when you have big regions, not a point, this may not be log n, because at some point you are taking one path and you may taking simultaneously different paths because they may be both intersecting. Okay, so since a query region may contain, for example, imagine this query region was like this. Okay, this is my query region. So at the root node, I need to continue my search both on the left child and right child. Okay, so you cannot filter out the one of the childs. It's not like binary search. Your recursive algorithm both calls the left child, search on right child, and search on left child. So how are we going to analyze the query time, the running time complexity? So how are we going to, is it possible that we intersect all the points? So can it be ON? Okay, so given a query region, I mean, it can be ON since this is, I mean, we are also bounded. This is an output sensitive algorithm. If the query region contains all the points, I need to report all the points, so there's nothing I can do. But even if the query region contains only k points, which is much smaller than n. Okay, can we still intersect n regions and query regions, and KD tree regions with an arbitrary query range? So can we provide a bound on how many regions a query rectangle can intersect with at most? So in order to do this analysis, we actually since we are trying to find the bound, we can convert this problem to something like this. Forget about this query region. Just bound, since the number of regions a query rectangle intersects is also bounded by the number of regions its left side intersects with. So number of splitting lines, how many splitting lines my left side intersects with, or how many lines my right edge intersects with. So if we can bound the number of splitting lines that intersect with the orthogonal window edges, then we can find how many of these regions that I'm going to visit. So we can provide a bound like this. So in order to do this bound, find this bound, what we do is we ask this question: how many splitting lines can an arbitrary vertical line intersect with? Okay, so given an arbitrary vertical line anywhere, how many splitting lines, or how many regions, not splitting lines, how many regions can this splitting line can go through? Okay, so this is the question we ask. For example, this splitting line, if it's to the left of this main splitting line, we know that n over 2 of them, it cannot intersect with more than n over 2. Okay, so a vertical line anywhere, I mean, put it anywhere, this put it on the left or right, this vertical line cannot intersect with more than n over 2. So a bound is n over 2, for example, but is it a realistic bound? Can we even reduce this bound? You can say it's n over 2 is again ON, so it doesn't help us much. We are still in ON. Can we? Is it a really realistic bound? So is it n over 2? Because the structure here also has a certain structure. For example, a vertical line is here. It cannot intersect the regions again here. So there are vertical splitting lines here. Imagine this was the case. Imagine all I had was just vertical splitting lines. Okay, divided by 2, divided by 2, divided by 2, divided by 2, like this. Okay, and when I give you a vertical line like this, first of all, the number of regions that it's going to intersect with. So if this is the main splitting line, 1, 2, this is 3, 4, 5, and 6. So it's first of all, if this is my vertical line, it's not going to intersect with these 2 regions. Okay, it's going to intersect with this main region here, and it's not going to intersect with this one. It's going to intersect with this and its child. So it's going to follow a path. So through this, so it's going to be log n. So if we are, it's like similar to one-dimensional range searching. Okay, you are following the largest, then its parent is smaller. The region you are going to get intersecting is going to get smaller and smaller. But the thing here is this is not a very good. Again, this is an over-optimistic bound because we also have horizontal splitting lines. Okay, the number of we don't only have we can intersect actually more regions than this. It's not only this, since we have horizontal splitting lines. So at the end, it turns out to be, if we write it recursively, the number of splitting lines that for n points, given n regions, it is given recursively as with this recurrence relation. Okay, what it does is the actual number of it skips a level. This n over 4 comes from the fact that the vertical lines appear at depth 0 and at depth 2. Okay, so it goes one more level to find how many actual to find the actual recurrence relation, and this recurrence relation solves to square root of n. Okay, so the query time, the running time complexity of KD trees, the query time is bounded, is O square root of n, and this is a bound, but it may not be a very tight bound, because what we assumed is that our query rectangle was really large. I mean, we assumed an infinite vertical line, and this square root of n is the bound on the regions which are intersected by infinite vertical line. So if you have a smaller query rectangle, you probably have your observed complexity is going to be much smaller than square root of n. But still, this worst case may happen anyway. So this you may have very large query rectangles which may give you this running time complexity, this worst case running time complexity. So this is how KD trees work. So the only thing you need to know is, it does after this lecture. What you need to remember is it builds a tree by alternating between coordinate axes, and it can also be extended to higher dimensions. If we have, for example, x, y, z, what we do is split on x, split on y, split on z, then go again x, y, z, x, y, z, x, y. So alternating between all dimensions. And it's the storage requirements of this, the index structure, it requires ON space. Okay, and it can be constructed in n log n time, but the final tree requires ON space. And the query time that it gives us is O square root of n. Now, I'm going to talk about range trees next. And range trees, I'm just going to take like 10 minutes to discuss about them. The difference from KD trees is that we don't have such an alternating structure. We build a tree on x coordinates, but each node in this tree have also an associated structure, which is another tree on y coordinates. So that's the okay, here's how a range tree looks like. First, we sort the points on their x coordinates, and we sort the points on their y coordinates. And the main tree, these are the range tree is also called a multi-level tree structure, because each node of the tree also has another tree, okay, which built on another attribute. So these are different attributes. These are multi-attribute, multi-level trees. So our binary search tree, our regular original binary search tree, is on the x coordinates of the points. We sort by the points, so we take the median. This is our root node. It has a certain x coordinate, x mid, and we have the actual points at the leaf nodes. Okay, the left to right order of these points are based on their x coordinates. Now, given the subtree rooted at this node, all the leaf nodes of this subtree, I mean, are called, I mean, these leaf nodes are called the canonical subset of this node, canonical subset of node V. Let me name this node V, okay? So, in other words, if I look at an intermediate node V prime here, the subtree that is rooted as this V prime, all the leaf nodes included in this subtree are going to be the canonical subset of V prime. Okay, so this is what we do. At each node splits the points with respect to their x coordinates. So here we look at x mid, and in the next level here we are again looking at the x coordinates of the canonical subsets of this half, and try to split them into two groups. Again, every time this original tree, we look at just the x coordinates. We don't have the y coordinates yet. But the important thing in, I mean, how do we do then two-dimensional range queries is that at each node, we have a pointer, we have a link to an associated structure, which is another binary search tree on y coordinates of the canonical subset of this V prime. So at this point, at this node V prime, we have another tree, let's say TV prime. This is the associated structure of TV prime, which is a binary search tree on the y coordinates of these points. So it goes like this. Each time, and we do the same, the search on range trees is exactly this, very similar to the search in the one-dimensional range search. Just imagine, for example, we have this range query. So this is our range, okay? X, Y, X prime, Y prime. So what we do is, on the original tree, we perform the exact same one-dimensional range query on X and X prime. So we look at X and X prime, whether if both X, for example, if X is greater than this X mid, we go right. So we find the splitting node. Until we find the splitting node, we again do nothing until we find the splitting node. And imagine this Vy prime is the splitting node. And after we come to the splitting node, what we were doing is that the X goes this way, X prime goes the other way, X prime goes the other way. And when we are going left here in this, whenever we take a left turn during this, after this split node, what we can safely know is that all the nodes on the right subtree are what? They are guaranteed to be within this interval in terms of the x coordinates. So what we were doing in one-dimensional search was that we report whatever we have here, we report all the canonical subset of these points. Now, we replace this reporting all the points with just do a search on the y coordinates on this canonical subsets. So you are going to have a subset in which their x coordinates are within the limit, but their y coordinates may not be within the limit. But you have a binary search tree on the y coordinates, so you do another one-dimensional range search on the y coordinates this time and report all the points. Instead of reporting all the points, you report only the points within y and y prime by doing another one-dimensional search on the associated structure. Okay, so this is the main idea of, since it's not a log n time algorithm because the original search takes log n and each of these subtrees again take log n, so the total is log square n. Okay, so the query time of this one is log square n. But there is a technique called, we can make use of the fact that the canonical subset of V prime is actually a subset of the canonical subset of V, right? I mean, if you have the parent node has a canonical subset, the canonical subset of a descendant node is a subset of the parent node. So, if we have a binary search tree on the larger set, can we conduct a binary search on the smaller subset efficiently? So this is the, can we get rid of multiple log n queries and make queries faster? And there's a technique called fractional cascading, which is exactly provides something to speed up such queries. The whole original subset contains links to these smaller subsets. And while you are doing search on the original one, you actually can find the exact location of the smaller subset as well. So while you are doing, so I'm not going to go into details of this fractional cascading approach. Just again, as a side note, know that this log square n can be reduced to log n with the help of using the fact that this canonical subset of V prime is a subset of its parents. So when we have a binary search tree on this, we can make use of the search we have already conducted here to speed up the search here. So it just goes from, after we find the search here, we end up at a node which is the smallest node greater than x, okay? When we are doing the one-dimensional search at a higher level, we end up at a node which is the smallest number greater than this left endpoint. And this is, this node in the upper level contains a link, to the number, which is again the smallest, the largest of the smallest numbers here. So we can immediately, in O1 time, we can find at which point we are going to start intersecting these y intervals. So we can go left to right or we don't need to conduct another log n time search in the subtree. So that's the main idea. So if you wonder more about this fractional cascading, you can read it in the book. It's, as I said, just the main idea is just link the original, provides pointers from the original numbers to the subsets, so these smaller lists. And the space complexity of range trees is not O(n) anymore. It's n log n because of these associated additional structures. Okay, if we didn't have these associated additional structures, the space would be O(n). If I have n points, the tree is going to have 2n minus 1 in total number of nodes, so it's going to be O(n) if I didn't have these associated structures. Since I have these associated structures, each associated structure is of size log n, so at the end I have n log n space complexity. So the space complexity increases compared to KD trees. Range trees consume more space. And they guarantee, with the help of using a fractional cascading, it can guarantee log n search time. So that's the whole about I want to discuss about orthogonal range searching. Do you have any questions? Okay, so let's have a break, a 10-minute break. Then we are going to start a new problem, which is locating points in subdivisions, planar subdivisions. How do you efficiently find which face a point is located in? So it's a different problem than this one. In this one, we had points, and we were trying to find points within a face, for example, within an orthogonal window. Now we are doing a reverse problem. We have faces arbitrary. They are not orthogonal. We have different orientation. We have a subdivision of the plane like a map. Given a point, find which face this point is contained in efficiently. Okay? So we are going to see a data structure which is going to guarantee log n time search in this